Thank you, Danny.
There you go, Nico and Toby.
Okay, so welcome everybody. Good afternoon for those that are in the afternoon. And thanks for the introduction. And I will be reviewing a little bit on the theory part of the non-minimal gravitational coupled scalar fields and how to implement it in a lattice formulation. I have to say that this lecture is based on Ben Stefanek's lecture notes that I think they are available in the web page of the last year. So also these lecture slides are posted already in the page of this year's school. So let's begin. So let me start by writing what would be the most general Lagrangian you can write down for a scalar field in a curved space-time. So as you can see, we have the action of the Einstein-Hilbert action, which is represented by just writing down the Ricci scalar. We have a scalar field with its canonical kinetic term plus its potential, and here I have what it's called the non-minimal couple of this scalar field to gravity, which is given by this kind of coupling, chi squared r, with this coupling strength C. Of course, as I told you, R here represents the Ricci scalar curvature, and in this case, for this Lagrangian, we choose to write the metric using the West Coast, as the US people like to say, the West Coast metric, which is the mostly positive metric signature. And in this case, the Xi represents the strength of the non-minimal coupling. So a little bit of motivation of why to study this kind of scenarios. Well, in principle, in a curved space-time and in general relativity and standard model, there is no symmetry that prevents us to write down this kind of couplings. As you can see, this coupling is dimensionless, and this has dimension 4, so there is nothing to prevent us to write this down. It respects all the symmetries, and we can just write it down. There is no problem on that. Even though, in conformal field theories, it's actually required to have a non-zero coupling, non-minimal coupling to have a conformal field theory of scalar fields in curved space-time. And actually, quantum mechanically, just having a zero coupling here is not stable, because at some point it will be actually generated through renormalization group equations in curved space-time. So these are the motivations of why to consider such scenarios. So whenever we write down or the Lagrangian in this manner, we call it the Jordan frame, where we can say that we have a scalar tensor theory of gravity, which is a scalar degree of freedom coupled non-minimally to gravity. So in principle, I can characterize this coupling with a generic function of the scalar field. For the case I was mentioning, of course, the function is given by this expression here. So usually, because of we have this non-minimal couple, is it common to study this in the Einstein frame? So let's check what this Einstein frame means. So one arrives to the Einstein frame by doing a conformal transformation, which is basically taking our metric and multiplying it by a function that should be continuous, non-vanishing, finite, and real, and should be arbitrary for any value of x. So by doing this, we are transforming conformally our metric. Here are some properties of the transformation rules in the dimensions. I mean, we can do this in the dimensions. Of course, we will specialize it to the case of 4 dimensions, but just to give you some rules of how it transforms the metric, the determinant of the metric, and of course, we can write down in 4 dimensions which will be the transformation of the Ricci scalar. As you can see, it's a large and complicated expression, but we will see that this will help us to do something. Why we are doing this? If we apply this transformation to the Lagrangian that I was showing you before, to the action, we get this. Of course, we have these conformal factors in front of all of our expressions. And what do we want is to recast this into a form that we have only Einstein-Hilbert action in the new frame. What it means is that whatever is multiplying or a rich scalar in this frame should be 1 and not this function or nothing else. So this gives us which are the conditions for the omega function to be. So in this case, for 4 dimensions, we want that the product of these two is equal to 1, so that such that whatever is in front of a rich scalar is equal to 1. So we are getting rid of the non-minimal coupling to gravity, or we are recovering just Einstein-Hilbert gravity.
Nico, sorry. There is a question,
Yes.
or someone raised up their hand. Sayak, please.
So in the normal transformation, why you're transforming like omega square x? Why not seeing it, not the function omega x?
Why do I get omega squared?
Yes.
Here?
Yes. Yes.
Well, I think that's a choice.
I don't understand. What's the question? Why omega squared?
And not just omega.
Yes, we can. Why not omega? We are.
You want to?
I think
you don't want to change. You want it to be positive, no? Well, probably that's. Yeah, there was.
Well, usually it's also written in some other form, like exponential to some function.
Yeah, which is
I think that's a choice.
No, it's the same as saying it's positive. I don't remember if you want it positive because it wouldn't change the physics to flip the sign, the global sign. You know. Yeah, I don't remember. Sorry. Yeah.
Okay.
But yeah, somehow we want not to change the signature, you know. But I'm sure there is a reason. I just can't remember right now.
Okay. Well, so if I actually take this into consideration, so I get rid of my conformal factor because now I have chosen that the f of chi is actually the conformal factor I want to recover Einstein-Hilbert action here. And I end up with these two, let's say, kinetic terms here, one for the chi field and one for this f. But actually, you know, f depends on chi, so I can actually, well, just to make sure that here I have dropped some terms that are just a total derivative. So, you know, I can drop terms when are like this in the action. So I can actually transfer, or let's say the derivatives on f can be write down as derivatives on chi field, and I can put this together and write down some factor in front of the kinetic term of the chi field. So furthermore, we can actually do, and we can put this into a manner that we have a canonically normalized kinetic term for the chi field. So I can redefine my chi field as well by choosing this, of course, and now I have defined what chi tilde is, and then I end up with what we all know, which is Einstein-Hilbert action in one side, and decouple, let's say, from decouple in the sense that it's no longer non-minimal couple from the scalar sector, and I have my scalar field with a canonically normalized kinetic term and its potential. But what is, let's say, what is now? I have just put things under the carpet. So let's see what are those things. I can actually write down the equation of motion for my non-minimal couple field. But what is the issue here is that actually if I want to obtain what is chi tilde in terms of my original field, is this very complicated expression. But we have a right to what we want to call the Einstein frame, and you can see that we have we just now have one scalar degree of freedom with Einstein gravity. So now we can use our machinery to study this. But let's see what are the problems. For example, just to analyze this solution, let's say, or this relation. For example, if I set the c equal to 0, I recover that chi is equal to chi tilde. That means frames are equivalent when I just go to the minimal couple case. For example, if I choose c equal to 1/6, I get what it's called a conformal invariant theory, I had this relation, and I get the potential transform like this. But how to understand this? In a conformal invariant theory, in this case, means that, for example, if I write down the equation of motion of the chi field in conformal time and with this conformal amplitude, I get that for the conformal invariant choice, which is chi equal to 1/6, it behaves as a free field. So this is what it means in this case. And I can also take another limit, which is also interesting, for example, for Higgs inflation. But so what are the problems here? Inverting the formula that relates chi and chi tilde is nonlinear. So there is some issues there. Also, fields are quantum. I haven't mentioned this so far, but fields are quantum, of course. And so there is no clear meaning about what the conformal mapping means up to the quantum level. So because we can, and I will show you how we do it, we can actually remain in the Jordan frame and study its dynamics there. So
Nice.
that's what we will do now.
Nico,
Sure.
sorry to interrupt. Can you hear me?
Yes, I am.
Okay, sorry. It's just I was thinking about this weight factor, the conformal factor. And the reason why we do it positive is because you don't want to change the causal structure of your coordinates. Essentially, this is a function of position and of time. And if you put it a linear function, the function can become negative for arbitrary set of regions, and you would be flipping
okay.
the role of the entries in the metric if you allow for that. You don't want to change that. You just want to do a conformal transformation, which is precisely not changing the causal structure, but just giving a dilatation, for instance, of the metric, and that's what you guarantee with a positive defined weight. Sorry about that. Just came to my mind and decided to tell you in this moment.
Thanks. Thanks for clarifying this. I think there is a question in the chat. Okay, no, that's the thank you from Sayak. Okay, so let's go back to the Jordan frame, and let's write it down again, or action in this frame where we have the no-minimal coupling here explicit, and I also allow for having extra matter sector here. So let's work on FLRW universe with the alpha time metric, and in this with using this metric, I can actually compute what my Ricci scalar will be for this given metric, and is given with this expression where I have to specify here what this curly h means. So the time derivatives here that you will show you in the equations of motions are with respect to the alpha time. So curly h is measured, let's say, in alpha time, is computed with the alpha time derivatives. So the relation with the actual Hubble rate computed with the coordinate time is given in this form. So just remember that the h curly h is not the Hubble rate, but let's say some kind of alpha time Hubble rate. Okay, I can variate my action for the no-minimal coupled field, for the chi field, and I can obtain an equation of motion, which actually looks very simple. It's like just having an extra term here that is proportional to the Ricci scalar. And if I write down this in the metric I have just chosen, it looks like this. So you can see, so again, it's the same equation that we are all used to, Klein-Gordon equation in an expanded background, with which as another term, what it could be seen as effective, some kind of effective potential given by its coupling to gravity. Now that we have the equation for the no-minimal coupled field, of course, we need to evolve this in an expanding background, for which we will make use of Friedman equations. So if I just said my metric is given by the FRW metric, that means that my universe is filled with a perfect fluid, and the perfect fluid energy momentum tensor is given by this form, where this pressure and then energy density depend on volume average over all fields present. And with that, of course, I can write down my Friedman equations, and the ones that I can use to evolve the scale factor, which is what I need for solving the dynamics, I can use the second Freeman equation, the one of the acceleration, and here I have this expression. So in principle, I have everything to solve my dynamics, to solve my equations, because I have the equation for the non-minimal coupled field, which you saw that it was easy, and I have the equation for my scale factor. But let's see how it looks, because I haven't told to you how it looks actually, the density, energy density, and the pressure whenever I have a non-minimal coupled field. This will change actually. And of course, I can write down my density and my pressure in this form, and you see that there is this part here that is the energy stress tensor of the non-minimal coupled field. That is something that we haven't checked yet. So let's write down this. Of course, I can get what will be the energy momentum tensor by applying the definition that we know, by varying the metric, by varying the action respect to the metric for the part of the action that corresponds to the non-minimal coupled field. And I get this expression here. We get what we expect from a minimally coupled scalar field. This is the energy momentum tensor that we all know, plus a part that belongs, or it's proportional to the factor of being non-minimally coupled. And as you can see, it actually contains curvature terms, which are encoded here. This is the Einstein tensor, which is a combination of the Ricci tensor and the Ricci scalar. So the tensor is not trivial for the non-minimal coupled case. So if I now write down what are the energy densities and the energy density that is given by this expression, you can see that I have what I was expecting: kinetic energy, gradient energy, potential energy, and terms that are due to the non-minimal coupling to gravity, that are proportional to the Hubble rate in alpha time, the chi-square volume average, this coupling here between the chi and its time derivative, and in fact I have this gradient here. And furthermore, the pressure is also given by this quite complicated expression. Okay, so to get the density, energy density, and pressure for sourcing the Friedman equation, it's going to be quite complicated. As you can see, it depends non-linearly on the scale factor and on various terms. So that is an issue here, because as I told you, in principle, I can just use the acceleration equation to evolve my scale factor, but the source of it contains nonlinear terms on the derivatives of the scale factor, and even though some surface terms. So is there a better way to actually evolve the scale factor? Let's check for another possibility. Let us remember what was the definition of R in the FLW alpha time metric that I wrote down at the beginning. Here is R, how it depends on the scale factor and its derivatives. Let's also take Einstein equation and just trace it. This is well-known, that if you take the trace of Einstein equation, you will get a relation between the Ricci scalar and the trace of the energy momentum tensor. And actually, because the trace is a linear operator, also this allows us to write down and to split the trace of the energy momentum tensor to be decoupled the non-minimal coupled field part with the other matter that could be present, other matter sector. And also, we can actually use this to tell what is the Ricci scalar if we just take a volume average of the trace part of the energy momentum tensor. So I now write down what would be the trace of the energy momentum tensor for a non-minimal coupled field in 4 dimensions. It is given by this expression. So I can just replace what I got here to this equation and solve for R. And of course, as I told you, because R now in the previous equation depends on a scale factor and the derivatives of the scale factor, in fact, R is computed from volume averages of the fields. So I have this expression that belongs to the non-minimal coupled part plus its contribution due to the another matter sector that could be present. So this is the key equation that will allow us to actually solve for the scale factor. So, and now we have everything set to write down a lattice formulation of the no-minimal couple field. So we have the equation of motion for the scale factor, which is given by the definition of the rich scalar, plus what we compute, which is how the rich scalar now is going to be sourced by the volume averages of the fields. And of course, we have also the equation of motion for the non-minimal couple field chi, which is a very simple one. Now that we have what our equations will be, we are going to rewrite this in program variables for CosmoLattice. So you know this, we have at least two scales, which is the F star, or the units in which fields are going to be measured, and omega star, which is some relevant energy scale of the problem. So in this case, you all know that now my potential in program variables is given by this, and also I can tell you that the rich scalar will be measured in units of omega star square. So for example, or for us in a particular choice we did to study this, we chose that we are going to measure the fields in units of the Planck mass and omega star in units of the initial Hubble rate of the system that we are going to simulate. And you will see this later, some results using this choice and why we choose this. So now that I have my formulation of what will be the equations of motion, I can write down the lattice formulation, or how are we going to evolve this. So again, as you know, I can define a conjugate momenta for my chi field. This allows me to write how it will be the equation to evolve the amplitude of the chi field. And if I write down this equation, this tells me how will be the equation to evolve the conjugate momenta of the chi field, which is given by this expression here. This is the kernel of the equation. You know, you see, it's very similar to the scalar field case alone, but with the no-minimal couple part being written here in a very easy manner. Now, the problem will be for the scale factor now. The scale factor equation is different of what we were using previously. So now I define what will be the conjugate momenta of my scale factor. This allows me to evolve the scale factor and to evolve the kernel of the scale factor evolution, which is basically the rich scalar that we will get from doing the computing this out of the volume averages of these expressions. Okay, so the rich scalar will be computed every time is needed from the energy, gradient energy of the nominal couple field, the kinetic energy, the potential energy of the non-minimal couple field, this expression here, that is the product of it times the derivative of the potential respect to the chi field, and here is basically the source due to the another matter sector that could be there. So this is the part of whatever other field that is minimally coupled to gravity. And here I show you how we compute actually these expressions. So there is an issue here that maybe you may have noticed or not, that actually R, the rich scalar, depends on all field amplitudes and conjugate momentum, because you see, R depends on the gradient energy, the kinetic energy, on the potential energy of all the field values at every moment. And also we have that the kernel of the chi field that depends on R, and R depends on the conjugate moment of the chi field. So that means that the kernel of the nominal couple field depends on its conjugate moment. So that means that we cannot use the symplectic evolvers that they were showing you, like a leapfrog or a velocity verlet. So we need to use non-symplectic evolvers. So like a Runge-Kutta one. So this is all. So now I have everything. I have written down what will be the lattice formulation for my field. And I think this is all for my part of the lecture. Thank you very much. And if you have any question, please tell me.
Thank you very much, Nico. Thank you very much. Okay. Yeah, there is still some time before we do the 5 minutes break. So please feel free if you have questions on this theory aspect. Yeah, maybe it's not so familiar to many of you. It depends on what you work. So meanwhile, you think of any possible questions. Maybe let me highlight that yeah, the whole point of, for instance, simulating this system is to see that, you know, there is to check that in reality we can solve the system without having to go to the Einstein frame, as Nico was saying, because typically people, in order to do analytical computations, they go to the Einstein frame because you know how to handle things in the Einstein frame. But what this shows is that there is no need. And actually, it isn't clear whether the two formulations are going to be equivalent given the quantum nature of the fields that are involved in the actual conformal transformation. And I think this example is very representative to give you an idea of how, once you know how the basic structure of kicks and drifts of CosmoLattice work, you can turn it into whatever evolver you want, into whatever interactions. You just need to write down what's the new kernel of whatever the interactions you want to deal with. And if you understand well the structure of CosmoLattice and you understand well your physics, nothing is going to stop you from implementing it and then being able to deal with the nonlinear physics as we did here, for instance.
I don't know if there is no questions.
Yeah, it's okay just to show the, you know, these are the new set of equations of motion, no, and maybe highlight again their intrinsic nonlinearity, no? Maybe you can comment on the, that the...
Well, yeah, like here the basic problem that one can easily see is how at the same time we need the information of R. R also needs to know what is the value of chi. So this for symplectic evolvers is an issue. So that's why we need to use Runge-Kutta implicit evolvers. So yeah, that is basically the whole issue about this system. That because R knows the information about all the matter content of the theory, it needs to know also of what it's sourcing. So yeah, that's the main problem here. Of course, I mean, you can actually try to do this for the linear regime. Actually, this equation, you can solve it in like in Mathematica or something in the linear regime, which means this coupling is not great enough, like to, or chi, I mean, chi is not great enough to back react into the expression or the evolution of the scale factor. So you can actually solve for this linear regime for the what will be the evolution of chi for this first stage. And that's what we do for, especially to set the initial conditions of this when we actually implement this to CosmoLattice. What else can be mentioned? I think there are questions in the chat.
Yes, there are a couple. I think the first question was addressed by Toby, referring to Ben's notes, and then there's another question.
Sí, so I will read it. In minimal cases, you have used the first Freeman equation. It's used to check the accuracy of the simulation, but here you are combining it with the second Freeman equation. Okay, no. So here, what I do to... So I still use the first Freeman equation to check whether my equations are... I mean, at least to check if energy is being conserved well enough, where I wrote down my equations. So what was used previously was to use the first Freeman equation to check whether the system is fine, that the energy is being conserved up to a certain level, and the second Freeman equation to evolve. So what I did here was not use the second Friedman equation but use the definition of R. So I don't I don't know if you can arrive to this equation by combining the previous two. I mean, I guess yes. But yeah, at the end, these are also independent equation from the first Friedman equation. So you can use this to evolve it and use the first Friedman equation.
The second one is really the computation of R in a Friedman-Lemaitre-Robertson-Walker. It's not
yeah, right.
Okay, it's not the Friedman equations. It's just that R in an expanding background, in an isotopy homogeneous animal, is a linear combination of the Hubble rate squared times the second plus.
Yeah, that's true. So yeah, I mean, the thing is, like, I can still use. I mean, this is basically the second Friedman equation that allows us to evolve the scale factor, and we can still use the Friedman equation to check on the energy conservation. We can do that. Yeah.
Yeah, but we don't evolve the scale factor. That's the key point with the second Friedman equation. That's precisely the point here. We do it with with this definition of R. And then we can still use the Hubble rate constraint to do our checks of energy conservation.
Okay, so
okay,
maybe
no we can take 5 minutes anyway, officially, you know, and come back at 45. But of course, if there are more questions, we can address.
Yeah, let's stay here.
Is my internet any stronger than earlier, or is it?
Now it's fine.
Okay. Let me. Can I share my screen and see if that causes my internet to move on, or if it's going?
We'll stop sharing right now.
Go ahead, Toby. Yes. Let's see.
Oops. How's that looking? How am I sounding?
You are sounding good, and it's looking good so far. So maybe the problem is solved.
Fantastic. Well, let's see how it goes. Do you see my mouse or not?
Yes. We see it.
Good.
All right, maybe we can come back. So welcome back, everybody. And now, after Nico presented the underlying theory, Toby is going to give us a taste of how this can be applied in certain scenarios. Toby, please go ahead.
Thanks, Danny. First of all, before I get cracking, I just want to thank Nico for filling in at the very last minute due to some family dilemmas that I had. Basically, I gave him the poison chalice. He's had to go through and go through all this theory without really, at least from my perspective, explaining why did we ever embark on this operation of simulating non-minimally coupled scalars on the lattice. And here, I really have to say, take a step back and say, first of all, I'm not an out-and-out cosmologist. My background is much more in particle physics. And so when it comes to these sort of modifications of the gravity sector of theory, I think I have a very different perspective compared to somebody coming at this more from a GR perspective. And so this sort of Lagrangian interaction that Nico introduced, where we take a standard scalar field and we couple it directly to the Ricci scalar, produces something, from my perspective, that's quite interesting. And this is essentially this idea that the size of this coupling is actually going to be, the size of this interaction is going to be proportional to how big Hubble is at the moment that you're asking this question. And so as soon as you identify that, of course, this Ricci scale is proportional to Hubble squared, then you start to think, well, these sort of interactions are predominantly going to be useful in the very early universe. And if you click and have a look through the literature on non-minimally coupled scalar fields, then of course you find this to be the case. Here, a lot of these non-minimally coupled scalar theories are predominantly looked at in the context of inflation and reheating. One of the things that I'd like to caveat for this talk is that I've done a thing that I think upsets Danny and a lot of other people quite significantly throughout this part of my talk. What I've actually done is I've used phi to be the non-minimally coupled scalar field and chi to be the inflaton. So this is the exact opposite of what Nico just presented in his part of this topical lecture on non-minimally coupled scalar fields. So please don't get confused, and just remember, phi is the thing with the goods, chi is the boring thing doing inflation. So out of all these sort of papers that I've collected below, these non-minimally coupled scalar fields basically play a number of roles. On this left-hand side, if you take the standard model Higgs field and you non-minimally couple it, then what this actually gives you is it gives you a new degree of freedom in the Higgs sector to essentially change the behavior of the Higgs field at large energies. And doing this can allow you to start to realize ideas such as using the Higgs to do inflation and reheating. Of course, there's still some difficulties in this sort of arena, but it's a very economical idea, taking the Higgs and essentially trying to do everything with it. And then on the right-hand side of this sort of list is more of a bunch of acute mechanisms for taking non-minimally coupled scalar fields and doing reheating. And so from this list, what I'm going to do is I'm going to just take one of these particular examples, and this is a rather old idea called geometric preheating, and show you what does this actually look like, and how have we realized it in CosmoLattice, and then maybe a few words at the end about what our next steps and future directions are in this sort of enterprise. So what is geometric preheating all about? Well, before we get there, we have to understand what is the actual mechanism that allows us to reheat in this setup. And so if we take our universe that's dominated by a single scalar field, And what we're going to be considering is we're going to be considering the epoch straight after inflation ends. Then as long as we're dominated by a single scalar field, we can easily identify what's actually happening in terms of the phase that the universe is in. So if this equation of state is -1 for the scalar field, then obviously our scalar field is basically an inflaton-like object. However, if it's oscillating around like an m squared phi squared potential, then it's going to be driving a period of matter domination. And for instance, another interesting potential you can build is also just, a stock standard phi to the 4 potential. If you have a scalar oscillating around that sort of potential, then you end up with a radiation-like scaling, even though you have no photon present in your theory. This is just a simple behavior where when we're oscillating around the bottom of a potential, we simply average over the oscillations and ask, what is the long-term behavior? So these three phases of matter are very commonly looked at. However, in the last maybe 5 or so years, there's been a real resurgence in this old idea of kination. And here, what actually happens is essentially you take a scalar field and you put all of its energy into essentially kinetic energy. And this causes the equation of state to hit 1, the exact opposite from inflation. Now, this is all well and good. I'm just basically rabbiting a bunch of stuff about if you have a scalar field, what can it do, and how does the universe expand depending on its behavior. However, from my perspective, there's quite a cute thing going on here. If you look at inflation to radiation domination, you start off with your Ricci scalar being -12 Hubble squared, and then as soon as radiation domination kicks in, it goes to 0. Not only that, if you were to engineer maybe a more complicated model, you can start in inflation and then end up in kination after your inflation ends. And what you're essentially seeing is you're seeing a change in sign of the Ricci scalar. And if we take a step back and remember that this Ricci scalar is exactly what we're coupling to the non-minimally coupled field phi squared, then essentially what we have from a particle physics point of view is it looks like we have some sort of spontaneous symmetry breaking that is induced by this sign flip of the Ricci scalar, aka the transition from inflation to kination. And this is exactly the lever that we use in this one of these previous papers on the previous slide, which we termed Ricci reheating. However, this is, of course, a little bit exotic because here what we're actually relying on is this period of kination. And typically, it's not so easy to realize kination, at least if you require a large amount of it. So for the case at hand today, I'm going to talk about a slightly more conservative way of leveraging this change in sign. And this is through geometric preheating. And here the idea is very, very simple. If I take quite a stock standard sort of inflationary potential, like an m squared chi squared, and then what I actually do is, given I'm oscillating around the bottom of this minimum, I can work out how my Ricci scalar evolves in that epoch. So the global picture here is, imagine I have some inflationary plateau for this chi field, slow rolls, and then eventually drops down into some minimum where it oscillates, and the bottom of this minimum is effectively described by m squared chi squared. In this case, I get an oscillatory Ricci scalar, and essentially a very similar idea is present to this Ricci reheating. As I oscillate around this minimum, I'm going to pick up both positive and negative values of the Ricci scalar, allowing it to change signs. And to better illustrate this is a small sketch. So in this big panel at the bottom is the Ricci scalar as a function of time. And I'm putting time here in my e-folds post-inflation. So inflation ends at 0. one e-fold, two e-folds after the end of inflation. And what I've also shown here is the top of this red band is 0. There's +12 and -6. So obviously, if you look backwards in time off to the left-hand side of this panel, you would see that I was inflating. So I was at +12. Inflation is then ending. And what I'm doing is I'm oscillating around, instead of a m² chi² potential, now I have a slightly more complicated inflationary potential. But the idea is still very much the same. If I look around small values of this hyperbolic tangent, then it's essentially a polynomial potential. So I'm oscillating around the bottom. And you can see is that I start to oscillate. I oscillate between these extreme values of -6 and 12. And every time I do these oscillations, what's essentially happening is I'm spending some time where the Ricci scalar is actually negative. And so now if I go back, forget about the inflationary sector, and then just ask, well, what's happening to my non-minimally coupled scalar field if, for instance, it doesn't have any other potential other than just this non-minimally coupled scalar field? Well, then what you end up getting is you end up getting a large positive squared potential when r is greater than 0. But as it flips, what you're going to start doing is your non-minimally coupled scalar field is going to start exhibiting periods of tachyonic growth. Okay, it looks like it's living in a potential that's unbounded. And so essentially what this is a way of actually reheating, transferring energy density from an inflaton to some other scalar field without there actually ever being direct interactions between them, other than through this dynamics and gravity. So that's more or less the main idea here. With this sort of sketch, then, we now want to take a step back and be like, well, what do we actually need to do to simulate the dynamics properly? And how can we use CosmoLattice to do that? So, of course, whenever we're going to be simulating these sort of early universe setups, we can't just start infinitely far back. We can't do 40-odd e-folds of inflation on a computer. So what we need to do is we need to come up with clever ways of choosing when to start a lattice simulation, and also working out what should my initial conditions be for said lattice simulation. So the first thing we need to do is simulate what's actually happening given this choice of inflationary potential, and nail down, the background evolution. So what we essentially need to do is, I'm sure many of you have already done this a million times, is solve the equation of motion for the inflationary field given this potential for a initial displacement of my inflaton. And so this is, of course, something you can just do in Mathematica. What we've chosen to do is we don't want to we don't want to simulate the entirety of inflation, because that just won't be feasible when we actually want to solve for a non-minimally coupled field. But what we want to make sure is we can span enough range of k-modes in order to realistically resolve a spectrum for a non-minimally coupled field, so that we can then feed this into the lattice simulation. So what we chose is we chose to actually simulate 14 e-folds when we solve for this background, inflationary background. And then using this, we basically initialize each of our scalar fields in Bunch-Davies. And then for each of the k-modes, we solve this differential equation. And the end result of which, we did this all in real time. We chose about 512 odd log space modes. What you essentially see in this panel is you have, on the x-axis, you have your k values, and on the y-axis, the amplitude of these specific k-modes. So at early times, which is this black line, so this black line is exactly at the end of inflation, and you see that you basically have Bunch-Davies. You have these two different power laws, depending on if you're at small k or large k. However, what you start to see is as you start to go to larger and larger values of time post-inflation, what you start to see is this occurrence of a peak. And here, this is basically just coming about because as your Ricci scalar passes through these negative values, you're getting periods of tachyonic growth. It turns out that this tachyonic growth is actually centered around a particular value of K on AH, just inside the horizon. Because here, this K value, K on AH for a given time, this would be the size of the horizon. And we see that for this particular choice of the non-minimally coupled valued C, we're about a factor 10 inside the horizon, where we get this sort of growth. Now, for all intents and purposes, you could say, well, Toby, you're done. Why do you need a lattice simulation? You've managed to solve both equations of motion. You've done it in a rather comprehensive way. And unfortunately, the problem here is that what we've essentially done is, if you were to consider this system in its entirety, these differential equations are coupled together. And so what I've done here is I've specifically engineered a case where my non-minimally coupled scalar field doesn't backreact on the inflationary sector. And so this is all well and good at the beginning of this period of growth. However, what happens is if I continue pumping more and more energy into this non-minimally coupled scalar field, then it's not just some small perturbation on this inflationary background, but rather I need to solve the whole set of differential equations simultaneously in order to get the correct results. And this is what we're actually interested in, because if I want to take my inflationary sector and dump the energy into some other sector and reheat, then, well, this has more energy at the beginning, but of course I need to take them to similar energies and then have the energy density in this other sector grow beyond that of the inflationary sector. So this sort of linear analysis, even with the decomposition of modes, is simply not sufficient to answer the question of what happens when this non-minimally coupled scalar field comes to dominate over the inflaton. Here, of course, I think I've presented quite a bit of information in quite a short period of time. So it'd probably be a good place to just stop quickly and make sure you have an idea of what am I trying to do with this model and what is the overall picture. Because if that isn't clear, then I'm just going to lose you even further from this point. So I see that there's one question. Can you unmute yourself?
Yes.
Yeah.
So, yes, I have a question. So this power spectrum, why this power spectrum, value of this power spectrum is larger than 1? Because you are working on the linear region. So is there any reason?
Sorry, you said that it's larger than 1?
Yes, this value is larger than 1, but you are working on the linear limit. So
he means the power spectrum y is larger than.
Sorry, what was that, Nico?
The power spectrum y is larger than 1. That's what I understood, right?
The amplitude, or
yes.
the amplitude is
amplitude of this power
amplitude is quite a fictitious. It's quite a random normalization.
Okay.
This
it is not
here,
correctly normalized.
No, it's not 100% correctly normalized. The main point of this figure is just to show you what the spectrum looks like when you finish inflation, and how does it grow.
Okay.
Because of course these tails out at large K, these are fictitious, right? This is just an artifact of how you initialize things in bunch Davies. So you need to subtract that to get actually at the physical result. And you've kind of shadowed my next point, which is perfect, because what we need to do is we need to work out, now that I have this linear power spectrum and it's grown a little bit after the end of inflation, what I need to do is I need to now devise a initial condition. And the fact that you have this growth in this very particular peak makes it very simple, because essentially all you need to do is allow for the peak to grow a little bit. So let's say take this, maybe this white, gray white region here. This is about 1 fold after the end of inflation. And you already see that there's been a lot of growth above this Bunch Davies result. So now if we take this result from here and we cut it off around about here, we know that this is a purely physical result, and we can use this to initialize our lattice simulation.
Okay, thank you.
Does this make sense?
Okay, and how many e-fold you are running in this case around?
I'm going to show you that.
Okay,
That's to come. But before I show what we're running on the lattice and the results, just seconds. Is this sort of picture about what's going on clear to everybody? That really there's an inflaton that's driving the Ricci scalar, and as a result of the Ricci scalar being coupled to this non-minimally coupled field, we're driving growth. Energy density is going from the inflaton to this non-minimally coupled field, essentially through gravity.
thank you.
Well, given the large amount of silence, either everybody is very confused, or I've set the standard for the lecture way too low, and people are bored to death. Either way, I'm going to plow on and essentially recap what Nico showed us. And so here he essentially derived all of these equations. But what I wanted to do is I just wanted to dump them on one slide, because ultimately this is the system of equations we need to solve. And as soon as you see it written down, you very quickly recognize that I'm not going to be able to do this in Mathematica. Not only that, but also we need to take a little bit of care over what is the choice of integrators, again, simply because of how the conjugate momenta and the definition of the Ricci scalar and how it enters in the equations. So at the moment we have an implementation of this in a private version of CosmoLattice. The hope is that we're going to make this public in a release in the not too far distant future. I know that I promised this already last year and I failed, but this is a new year, so we'll see what happens. So this is all implemented, and the way it's implemented is really super simple. Essentially, there's only a couple of differences. So if you open your normal sort of model file, then essentially what you need is you need an extra line that basically tells the model file, out of all the scalars that you have in your theory, which of them are non-minimally coupled to gravity. And so here in this particular model, I have only two scalars. I have an inflaton and this spectator field phi. My inflaton I've chosen not to be non-minimally coupled, so that's the false. The second piece is true, and that corresponds to the phi field, the guy I do want to be non-minimally coupled. Then the rest of the model file literally proceeds like normal. You define the potential, you define your units, you define all the derivatives that are necessary, and some constants and Planck, the usual jazz. I think that's from memory everything that's present in that model file. The next things are then what actually changes in the input file with this non-minimally coupled field. And so here, to reproduce the results of what I'm about to show you, there's literally only two things that need to be changed in the input. The first is you need to pick a value for the coupling in front of the non-minimal coupled term. You need to pick a value of C. This probably wasn't emphasized enough by me, but it's dimensionless coupling. It's also a classical field theory, so it's not quite this whole idea of unitarity and a 4 pi limit that we have in quantum field theories is not quite as rigorous. So values of 10 or 100 are just as good as values of 1 or 0.1. And last but not least is we, for this case at hand, we also need some sort of input power spectrum. And for this particular purposes, I hope Danny or Nico can correct me if I'm wrong, but I'm pretty sure that this power spectrum reader has been made public now. And so literally all you need to do is put these sort of results that I've shown here, amplitude against K, in the right units, which always confuses the hell out of me. But once I go back and consult the manual, which has all the correct units for these guys, is usually not too difficult to work out and not screw up.
It's not public yet, though, the from power spectrum arbitrary shape, but it's one of the things we were thinking to release before Christmas, if possible.
Okay, thanks for the correction, Danny.
Yeah, one comment I would make is, although it's true we follow the classical dynamics, this is as quantum as you get in any particle physics or any other perspective, because the initial condition of the field, it's really mimicking the quantum fluctuations. And it's simply that we can go beyond the linear regime because the system has become classical, but the values of the psi, if one has constraints or prejudices about how large they can be based on, particle physics aspect, they could also apply here. The thing is, in my opinion, there is no real law that forbids you, to have large couplings other than naturalness, which is not a law of nature, it's just an argument, Just wanted to make that clarify, but it's not like we are doing something different from you would do, from particle physics. It's simply we can follow the dynamics once it becomes nonlinear. I hope you agree, Toby, but otherwise...
Yeah, no, for sure. I mean, it's a more elegant phrasing. I was just using the caveman phrasing. Because in essence, this whole idea of squeezing the energy out of the inflationary sector, you're amplifying something. And the question is, well, what are you amplifying? And what you're doing is you're amplifying these quantum initial conditions that we chose through Bunch-Davies. Because, a big number times 0 is still 0. So there needs to be something that you're amplifying. And that's exactly these quantum initial conditions that are then becoming classical. And then we're using a classical lattice simulation to track them further. So enough chat. What does the outputs look like? I'm just going to show them all here. So the differences is that in the scale factor file, you now have an R kicking around in the last column, which is very useful when you're doing this business. The power spectra outputs are exactly the same. And the big changes actually come in the average energies. So there you have not only the usual kinetic gradients, potential terms for the different scalars, but now you also have these additional pieces that arise for a field that's non-minimally coupled. These additional contributions to the energy density, rho phi, which are these terms down the bottom here, which I've labeled NMC1 and NMC2. The last one is can be expressed as a total derivative, so actually doesn't contribute. So it's only these two additional pieces that we actually have to worry about when we consider a minimally versus non-minimally coupled scalar field. And if we do the business now, this is essentially what you start to get. So in the solid line is the results from the lattice simulation. In the dashed line is the result of my linear power spectrum analysis. And so from memory, we chose to initialize this simulation at about an E-fold after the end of inflation. So this bluey purple line. And so you see, of course, that at the beginning, they agree superbly up to discretization effects at the larger length modes. Then as time evolves, you see the agreement is still very good. But then once you start to hit about 2 E-folds, you start to see that really the wheels fall off the wagon, and the lattice simulation is giving you something that looks very, very different to the linear analysis. And here, what's actually the case is the lattice simulation is correct, and the linear analysis is completely wrong. And the reason is that now there's in this space of one e-fold, is I've pumped enough energy into the non-minimally coupled sector that now its energy density is comparable to that of the inflationary sector. And this, of course, signifies a breakdown in this linear analysis I did where I sequestered the two sectors. And so you can very easily start to see this if, rather than showing you a power spectrum, I show you how does the energy density evolve. And so before you look at all these 10 trillion colored lines that I've put in this figure, what you need to look at is the red and the black. So the red is the energy density of the inflaton, and the black is the energy density of the non-minimally coupled field phi. So at about one e-fold, when I start my simulation, you see that there's a huge hierarchy between the two. My linear analysis is great. I've committed no sin. Everything is good. But then what you see is the tachyon is incredibly efficient at driving energy density, and you see this very steep growth. And this steep growth, it continues until you get somewhat close and is mediated, is a small turnaround. And then essentially what's happening is you are going through a region where actually one of these contributions that are beyond the minimal coupled energy density, one of these becomes to dominate and is actually negative in sign. So this is the reason why there's a transition from a solid to a negative line, just to be able to illustrate when the energy density of the NMC field is positive versus negative on a log plot. I've just chosen to use this alternate, what is it, line style? That's the word. So you see in the black
Dash line,
thank you. You see the black dashed, and you see that this is predominantly driven by this purple dashed line, which when we go and consult the this guy here, you see that, oh, it's a term that is basically a lattice average of the field and its alpha time derivative phi prime. So intuitively, this makes a lot of sense depending on the potential you're considering. You can, of course, have a negative derivative here. And so it's not at all inconceivable that this guy is actually negative. One of the things I do want to point out is that due to having a non-minimally coupled field, you don't satisfy all of the energy conditions that you expect in normal general relativity. However, you don't violate any of the big ones. And so what these energy conditions are telling you here is that even though one of the components of the universe is going negative, if you sum up all of the components that are present at that time slice, what you find is that you still have a positive energy density in the universe. It's not like all of a sudden the universe is turned over, has a negative energy density, is going to do something crazy. That's not at all the case. Here it's just one of the subcomponents is negative. So, so what you see is that you this sorts of oscillate and fluctuate, but what you see is that if you average, you see that the black slope is less steep compared to the inflationary slope, and you see that at larger values of time, that this black is slowly coming to not completely dominate, but at least have a comparable energy density. So this is the case for this sort of hyperbolic tangent to the 6 inflationary potential with a non-minimal coupling of around about 50. And so what you can see is that depending on, this was the case in the previous plot for if this non-minimally coupled field has no potential whatsoever. So its potential dynamics are driven purely by this coupling to the Ricci scalar. However, of course, we know in any sort of particle physics models, scalars without potentials don't really exist if they're coupled to anything at all. And so we can then start to play the game of, well, how do things change when I add mass terms or quartics? And so for this, the black is again the case with no potential. The purple is if we add a Hubble scale mass. So H star refers to Hubble during inflation. So if this mass is a couple of decades below the scale of inflation, what you start to see is that you still get this initial tachyonic growth, but excuse me, at some point, what happens is you start to feel the effect of the mass in this potential. And eventually, rather than continuing to track the red line, eventually you come to dominate over the inflationary potential. On the flip side of the coin, if you have some sort of bare quartic for this spectator field phi, then what you see is that as you drive this field to larger field values, what's eventually going to happen is that this quartic is going to dominate, and it has the effect of regulating the tachyonic growth that the field experiences. And you see this from the fact that before you get to the top here of this peak, you essentially hit a plateau and you start oscillating around the quartic. And so this is a real big dampener in terms of your prospects, essentially, of using it to reheat the universe. So last but not least is I just want to show you a more clear picture of what's actually happening in terms of what is the field values for this non-minimally coupled field as it's getting driven. So what I'm showing here is on the dashed lines are again the result of this linear analysis, and the solid lines are the result of the lattice simulation. So you see that the lattice simulation starts at an E-fold, and what you see for large values of C is you get this tachyonic growth, and of course, because I've decoupled the two sectors, it just continues. There's no back reaction, there's no knowledge about the total energy in the inflationary sector. It just keeps growing and growing, which is of course completely unphysical. However, when you solve the full system of differential equations together, what you see is growth, but what you see is you clearly see some sort of asymptotic behavior where the field excursion through this like tachyonic growth obviously doesn't exceed m Planck. Here you see I've snuck in a cheeky m Planck squared in the denominator to normalize these field excursions. So you see that, of course, for these large values of the non-minimal coupling, doing the full lattice simulation is very important. On the other hand, if you have a smaller value of C, you see that the lattice and the linear analysis agree very well with one another out to large times. So as you can see with this sort of lattice simulation, again, you can't simulate these dynamics for like 10, 20, 30 E-folds. You're really constrained, depending on how much computer time you want to burn. You're really constrained to a handful of E-folds. Of course, this also depends on exactly what it is, what are the differential equations you're solving, what are the dynamics. There's, of course, certain scenarios, and I think Danny's done quite a lot of work where they've actually pushed the envelope for how long you can actually simulate. But for the cases at hand here, 4 or 5 E-folds were more than sufficient. So in my last 5 minutes or so, what I would like to just mention is just what we're doing now and where we're going. Of course, in these sort of situations where you have this extremely violent growth of the field, the first question you can ask is, well, surely these large gradients must source gravitational waves. Unfortunately, a bit the problem is that you now have quite an exotic background. And defining what is your dynamical degrees of freedom in a gravitational waves is much more complicated. So this is something that needs to be worked out carefully for an implementation into CosmoLattice, but would be extremely interesting in order to study. Whoops, and of course the window went away. Of course, would be extremely interesting for understanding what actually happens and if any of these sort of setups could be discoverable in gravitational waves. Of course, like most sort of inflationary or post-inflationary setups, there's usually a bit of an issue in terms of the frequency being a bit high. But because this is such a fast way of reheating, there's always the hope that you could maybe push the frequency down to really push the scale of inflation down a little bit and have lower frequency gravitational waves that might be within reach of experiments. Second is, well, we've done this now for toy setups like this geometric preheating, Ricci reheating. Of course, now you want to go and consider the case where actually you non-minimally couple the Higgs field, and it does exactly what I've just explained to you in terms of this dynamics. That instead of just pumping energy into some random field, you pump it into the Higgs. The Higgs fragments, produces tops, W's, Z's, and in that manner, you reheat the universe. Of course, this is no small task. There's a lot of gauge fields that are very relevant, as well as the fact that the Higgs has a known potential as a function of energy that needs to be consistently incorporated. And last but not least, you can then also start to study constraints on what is the size of this non-minimally coupled Higgs, given the idea of an oscillating inflaton. Of course, we know in inflation, if you have the Higgs as a spectator, certain values of this non-minimal coupled field will lead you to probe catastrophic regions of the Higgs potential. So the idea here is that potentially, if you study this after inflation, there's also a bound in the opposite direction. And so these are the sort of directions we're looking into, and using CosmoLattice to actually make solid predictions about what's going to happen in these sort of setups. So I think at this point I'll stop, and if there's any questions, we've got lots of time. So thanks for your attention, everyone.
Thank you, Toby. Thank you for the presentation and for being on time. Good. Please, well, we can stick here for a while, and hopefully there are some questions.
I choose to believe if there's no questions, I've done a fantastic job, and I'll just pat myself on the back rather than the opposite. I mean, how has it been in the last last couple of sessions? Have you had lots of questions, or have people been a bit Zoom shy?
Yeah, no, this was, I mean, your lecture was more kind of a seminar, so it's a bit different from the previous one.
Yeah. I just definitely gave everybody a good blasting of information. But I hope that it just gives you some insight as to, you can really push the envelope of this software package, and it's really not, you don't have to go and reinvent everything from the ground up. Things are quite modular. Adrian's done a lovely job of coding it. And so you're not going to have a miserable time.
Okay, one question. Tucker, please go ahead.
Yeah, I have a question that's related to the non-minimal couplings you talked about today, but not in the context of a Ricci scalar coupling. And this is a kind of a specific question, but I've been working with a model that has couplings between real and complex scalars and the field strength tensor for a U1 field. And I know, of course, that it's really straightforward to have potentials between the scalars. You guys have shown that case today, but I'm curious if that's something that would be particularly challenging to work.
In CosmoLattice or in general?
In CosmoLattice.
Yeah. Can you repeat what is the case, Tucker? Sorry, that you are considering. What is special?
Yeah. So I've got like one of the couplings is the equivalent of phi squared F squared, where F is the U1 field strength tensor.
Yeah, of course. Yeah. Mm-hmm. No, that with Runge-Kutta, it's absolutely doable. We haven't tried that scenario in CosmoLattice, but other people have done it in the past with Runge-Kutta integrators. And to my knowledge, depends on the context, of course. In principle, there is no problem whatsoever.
Okay.
It should be easy to generalize in CosmoLattice with the Runge-Kutta integrators once you are familiar with how to use the code.
Right. Thanks, Danny.
I mean, in a sense, if you want, it's very similar to some extent to what Toby has been presenting, except now that you are modifying the non-canonically the kinetic term of gauge fields propagation. No, it's been done, so I don't see what would be the difficulty here, other than it needs to be implemented. Yeah.
Very good. Yeah, thanks.
But correct me if I'm wrong, Danny, but usually in the model files, you don't specify the kinetic term. So you have to be a bit more in the model files. So you have to actually go back and change some stuff in the...
In the model files, if it's a scalars or the standard canonical gauge theories, you don't specify that, of course, because that's the information you have in the kernels, which assumes a given dynamics, you know. But that's the thing. If you have a different dynamic, then you have to change the kernel for that specific scenario, you know, which is pretty much what we did for the non-minimal.
Yeah, write down the equation of motion and work out what needs to change.
Yeah.
And in the end of the day, to do this, to make these changes to CosmoLattice, I mean, aside from adding in some new integrators and a way of reading in the initial spectrum, I think there's maybe an additional 20 lines of code. Maybe less, maybe 10, 15. There's really quite small modifications.
Yeah. No, I think it's very interesting, for instance, the example of Toby and Ben, you know, who might come more from the particle physics side, and then jumping into the code, you know, and in no time we were essentially putting together all the ingredients for working this non-minimal coupling to gravity. And of course, it is some work, you know, it's not as straightforward. It's what we are saying all the time. No? If you want to add new physics, it requires some work to adapt CosmoLattice to do so. But it's absolutely doable once you know the language and the structure of the code, you know, and who stops you there? You can do whatever you want, essentially, almost. Yeah.
What was the plan next? You had a Q&A after this, right?
Yeah, I mean, this is pretty much it. You know, typically when we finish every lecture, we just stick here for a while. Every day's lecture, yeah, we wait here if people want to discuss aspects, which can be, of course, aspects now of the morning sessions as well.
You know, just people haven't got enough Zoom in their life these days.
Yeah. I've got to say that I do prefer maybe to go for in-person schools next years to come. You know, yeah. It's this Zoom thing. Yeah.
Yeah, of course. Seeing people's faces is very helpful for working out if you've confused everybody completely.
You've confused them enough. Adrien, bonjour.
Hey.
Hello, morning. Good, guys. So, well, we are happy to wait the other 5 minutes in case somebody has really some question. Otherwise, in any case, we are going to reconvene tomorrow, 9 a.m. In Europe, 12:30 in India, 2 p.m. No, 3 p.m. in China. And tomorrow morning, or at least Europe's morning, we are going to have our last practice session where we are planning to give some examples with gauge fields excitation, including abelian and non-abelian, but also, of course, in case there are questions from the attempts of your runs on the previous days with the scalar fields or gravitational waves, we want to give some room because it's going to be the last opportunity to have a discussion. And then we'll have another Fino lecture, which will be, again, more like applications. That'll be an action inflation. And finally, in the afternoon or last session of the school, we will have some perspective discussion on lattice simulations. Although for half an hour, the half an hour that we couldn't cover this morning with Adrian, he will give us some, taste of the structure of the code. So you can say goodbye to the school with a final view of what is the tree three-folder structure of the code of the different parts in case you really want to go into modifying inside the code. Good, I see no questions. No, there are questions. Yeah, there we go. Alexei, please go ahead.
I was wondering if you just permit me a theoretical question on the non-minimal coupling. So for a while there, I think there was a notion that there was unitarity breakdown, a unitarity violation in Higgs inflation models or preheating following Higgs inflation. But I think implicitly from your talk, Toby, has this view changed in your opinion, or is there a flaw in this argument that's been realized recently?
Danny, do you know a bit more about Higgs inflation? Because
Yeah,
I have not been following.
I can answer that.
I was always, my perspective at least, was always, you add this non-minimally coupled coupling to the Higgs, and you end up with a plateau often large field values where you're like grand. But then to actually get to the lecture weak vacuum, you had to cross through a part where your conformal mapping between the Jordan and Einstein frames breaks down. And my understanding was this is one of the things that is kind of really unsatisfactory in those sort of setups. But Danny probably has a more nuanced opinion than I do.
No, the thing is, you have to realize, Alexei, that what Toby was presenting is not really axion inflation. It's a spectator field, if you want, So essentially, this guy only dominates the energy density after the end of inflation in this setup, and it doesn't suffer from this unitary problem as it happened in Higgs inflation. To be honest, there have been several back and forth on Higgs inflation about the unitary problem, and there were ways to unitarize, but the major problem was really that the self-coupling of the Higgs turns negative at the energy scales of inflation, and also you lose control of the theory at that energy scale. Essentially, you should get a power of a series power of a power series of other operators that had not been considered. However, in what Toby was presenting, here is just a spectator field that initially plays no role whatsoever during inflation. And it's only later on that it sucks up the energy out of the inflationary sector. And to my knowledge, there are not the same conceptual problems. That could be the issue of the self-coupling of the Higgs. Turning negative depending on the energy scale. This could still be an issue if you think of the non-minimal coupled field as the Higgs. But if you think as an arbitrary non-minimal coupled Higgs, which could be a singlet of the standard model, then this is not a problem in principle.
I mean, there you're just worried about what the scale of inflation is versus the instability scale of the Higgs, right?
That's right. And indeed,
okay, thank you.
I'm not sure was totally satisfactory, Alexei, but just to distinguish, that Higgs inflation is a very, very special setup where the Higgs is responsible of inflation. And now what we know for certain is that the Higgs as a field exists. And if it exists and there is inflation, there are very likely phenomenology like the one Toby is describing, not necessarily, of course, this depends on the model of inflation, but the fact that the Higgs exists, it means that it's going to get excited either during or after inflation immediately, and a non-minimal coupling is a very, very natural ingredient to have compatible with all the symmetries and so on.
Well, I think the interesting view with the non-minimal coupling is that with C, you have a choice of the sign. And so what you can always do is you can choose the sign such that it could be damped and not excited during inflation. But if you do that, then when the Ricci scalar changes sign after the end of inflation, then it's going to be excited straight after the end of inflation. Or you can do the opposite way around, pick the opposite sign, and it gets excited during inflation and not after the end of inflation. So it always seems to me that unless there's big bear terms in the Higgs potential, then no matter which way you pick this, there's going to be some sort of shenanigans that the Higgs is involved in, even as a spectator.
Yeah, I think so too. Yeah, I think the fact that the Higgs is a scalar field, a fundamental scalar field, is what provides this nature. That but it's difficult not to get it excited. It's difficult to prevent its excitation. Essentially, yeah.
It's difficult to make it heavy all the time and then also have an electroweak vacuum.
There's a question here. Organization, when there was word about the Slack channel. If I didn't get it wrong, is this public? Yes, yeah. Of course, you could use it for next questions in the future. Yeah. I'm personally not a big user of Slack, but I mean, I think we created with the idea that if people start, making their own progress, you can raise up doubts there or discuss there. And of course, you can always reach us by email if you feel we are not reading something that is being addressed to us, the organizers or developers of the code. Yeah.
Where can I find it? Can I just search for it?
In the emails we sent to the participant list. You didn't get this email, Christopher?
I'm not sure. Maybe I didn't read it until the end. That's possible.
Yeah, no, it's in the email. But okay, good point. I can put it in the website anyways. Of course, the link. But,
yeah, would be great.
Yeah, but it's in the email in principle. So a lot of people sign up. Yeah, but I don't think people have been commenting so far things there. Yeah.
Great. Thanks.
No problem. And also notice that the videos are available if you Google in YouTube CosmoLattice school, you will find the videos.
Yeah, I was already on YouTube.
Excellent.
Awesome.
Good. Is there any other question? If not, we leave it here and we reconvene tomorrow. Thank you very much for joining us and see you tomorrow. Take care.
Thank you very much.
Have a good